Hey everyone, I'm Seto. I am a site reliability engineer over at Cockroach Labs, working on the Cockroach Cloud team, and today we're going to be talking about running a distributed system across Kubernetes clusters. We're going to start off by talking about how much easier it has gotten to run software on Kubernetes in the past few years. We now have dynamic volume provisioning and stateful sets, which makes deploying databases significantly easier. We now have multi-zonal clusters, so we can deploy highly available software, at least when it comes to a single region deployment. We have managed Kubernetes services, so we can actually pay someone else to handle the task of running these master nodes and handling the upgrades for them. We also have Helm charts and customize so that we can have more reusable deployments that we can even package up and send over to consumers of our software. And on top of that, we now have operators too, which do a lot, but in its simplest form, it provides users a way to give a slightly more understandable form to how they want their software to be run, and then the operator handles translating that into the more complex Kubernetes objects. However, if you have an application that is deployed across multiple regions, you're going to find that these quality of life improvements hasn't really given you all that much. You're going to find that the deployment of individual regions is gotten significantly easier, but deploying your system as a whole is still fairly complex and difficult. And there's been a lot of great work and progress even towards a production version of federated Kubernetes. However, we have multi-region deployments here today, and we need a solution that works now. And that's what we're going to be talking about today, is things that we've kind of patched together to make this work in the interim. Before we really dive into the how of running multi-region applications, let's talk about why we would even want to do this in the first place. And reason number one here is going to be latency. Let's say, for example, I have this hot new startup that is developing an application for first responders. And we're going to start off by deploying this in the somewhere on the East Coast. And let's say somewhere in Kentucky, there is a car accident. Now, the nearest data center to Kentucky is likely going to be somewhere in North Virginia. The hop over there isn't going to accrue much latency. However, we have a very successful startup here, and we've branched out into California. And now somewhere in California, there is a breaking and entering. Jumping all the way back over to North Virginia is going to provide a fair bit of lag in the information getting over to the first responders, and this isn't a situation where that's really acceptable. Suppose we even make it out to a global scale, and down in Sydney, Australia, someone's having a heart attack. Jumping all the way over to North Virginia again is not really an acceptable amount of time to spend when you're dealing with a situation of that nature. However, if we can be deployed in multiple regions, we ensure that the data center we're jumping over to is always the closest one to us physically, thus reducing the latency required to use our application in the first place. Next up here is going to be fault tolerance. So let's say, for example, for whatever reason, there is a cataclysmic event in the West Coast that just takes down all cloud services simultaneously. This is going to bring down our application, traditionally speaking. However, if we're in a multi-region setup, then this isn't really going to apply to us. We'll still have these other regions up and running, and generally speaking, I wouldn't really consider this to be a realistic case, but given how this year has gone, the list of things that I consider to be possible and impossible are seeing some rearrangement, unfortunately. So back to our situation, the entirety of the West Coast has gone down, has gone dark, and all of our first responders, let's say they still have internet access. Because of this guy on Twitter that really likes shooting things into space. You know the one. Anyway, so they have internet access. They can still find out what's going on in their situation by just jumping over to the next data center. And we're not accruing that much latency just because we're a few states over. Sure, it's going to be a bit slower, but we still have a fully functional feature, which, all that to say, multi-region data center or multi-region applications are going to save lives. Or at the very least, we're going to be able to watch memes faster, which is pretty cool too. And finally, with all of that meme and or first responder data, that's going to be subject to GDPR, everybody's favorite regulation. And regardless of really how you're handling this, you're going to have to be deployed in multi-regions in some sense of it. Your data is going to have to be dispersed into the regions in which your users are currently in. So rather than having everything pipe through one region and then jump out to others, it's easier just to have it be in all these multiple regions in the first place and just stop it from crossing into these other regions. So again, this is more of a why slide, and it works a lot better with a live audience because we were going to ask this question. Everybody would raise their hand, or a lot of people would raise their hand, and we'd ask another question. Most people would put their hands down and we'd be like, yep, so everyone's kind of interested, but it seems difficult. For obvious reasons, we can't really pull that gimmick anymore. So pretend like that happened and it was really cool. And we're going to move on to what makes this such a difficult problem to solve anyways? That's because a multi-region deployment and a multi-Kubernetes cluster deployment are effectively synonymous. You are more than welcome to try and deploy a single Kubernetes cluster across multiple regions, but your mileage will probably vary and not be very good for that matter. And also, this is really because Kubernetes was not designed to span multiple wide area networks. Originally, it wasn't even meant to span across multiple availability zones. But the community, we fought for that. We got it. We won. Huzzah. We can deploy high availability applications, provided that, our region does not go down. To better understand the requirements of a distributed stateful system, we're going to take a look at Cockroach DB. Hopefully you've heard of us. If not, Cockroach DB is an open source distributed SQL database. Some of our key concepts are that we use standard PostgreSQL. Data is then chopped up into these chunks we call ranges that are replicated and distributed across the entire cluster. Nodes hold on to these ranges, and if they are spun up, spun down, or crash for whatever reason, then the cluster will automate the redistribution and replication of these ranges to ensure that all your data remains highly available. We use the Raft consensus protocol to ensure serializable transaction isolation. And finally, we have the concept of locality for data. So data can be tied to a specific physical, logical, or real location, which, as luck would have it, is pretty convenient for GDPR compliance. So here on the Cockroach Cloud team, all of our managed instances of Cockroach are run on Kubernetes. And what we need for Cockroach to work well on Kubernetes is roughly three things. We need every pod to have some form of persistent storage that is going to survive restarts. Every pod also needs to be able to communicate with every other pod in the cluster. And finally, we need a network address for these pods that is going to survive across restarts. And this is a pretty loose list, but we're comfortable saying that this applies to the majority of distributed systems out there. And when we're running in a single region, these are very easy guarantees to provide. In fact, this is exactly what a stateful set provides us with. However, when we get to the multi-cluster story, things get a little bit more difficult. Ensuring that we have these persistent network addresses across our clusters gets a little bit difficult. And if we're not running in the same cloud environments, or we don't have VPC peering available to us, having nodes be able to communicate with each other is pretty sketchy at best. And this all really boils down to networking in some fashion. We need to ensure that we have pod-to-pod communication across our clusters and within our clusters. And we also need these persistent addresses that work, again, both within and between our clusters. So this all boils down to networking in some fashion. We need to enable pod-to-pod communication across clusters, and we need to guarantee that we have these persistent addresses that work both in our cluster and across our clusters. And this final point can be weakened a bit to just a pair of addresses, one that works for intra-cluster communication and another that works for inter-cluster communication. However, this doesn't really solve anything for us. It just widens the number of solutions that we have available to ourselves. Again, before we start to look at the various solutions available to ourselves, we're going to take a slightly closer look at how Kubernetes thinks about networking and how that has affected our multi-cluster networking story. So Kubernetes doesn't really care how networking is done, it just has a few requirements that need to be met. And those are that each pod has its own IP address. The IP address that a pod sees itself as needs to be the same IP address that other pods see it as. And finally, all pods need to be able to communicate with all other pods without any form of network address translation. And traditional networking setups make this a little bit difficult as they only allocate 1 or 2 IP addresses per host machine. And on Kubernetes, we're looking to be running in the order of tens of pods per machine. And in lieu of this, we've had a lot of solutions kind of pop up here. On the Kubernetes networking documentation page alone, there is at least 20 some odd solutions that are available to us. And unfortunately, besides the 3 requirements that Kubernetes has, these various networking solutions don't have that much in common. In fact, not all of them even enable pod-to-pod communication by default. Some of them will have it be kind of easy to turn on, and others you're going to have to jump through some hoops to even make it possible at all. And that's going to add just another layer of complexity onto some of the solutions that we have here, as they require the networking solution you have chosen to enable pod-to-pod communication. And we are finally on to the solutions part of the talk. However, we are taking a quick pit stop by the disclaimer slide first. Disclaimer number 1 is that we are not here to prescribe one solution as the way. All of these options that we're going to be talking about have a drawback in some way, shape, or form. Disclaimer number 2 is this is not an exhaustive list. If you have a specific solution that you're hyped about, or you're even working on a specific solution that you do not see in this slide deck, it's not that we don't like you, it is just that your specific solution did not cross our radar while we were making this talk. And finally, disclaimer number 3, our requirements are slightly different. We are looking for a solution, or set of solutions rather, that we are comfortable deploying on Cockroach Cloud to manage our mini multi-region environments. And we are looking for solutions that we're comfortable with suggesting to customers to run in their own Kubernetes environments. So we have a few more things to be thinking about in terms of reusability. All right, without further ado, we have solution number 1, which is static pod placement and host network. Now, this is going to look very similar to a traditional bare metal deployment. We're taking these individual pods and we're going to be tying them to specific machines and the IP addresses of those machines by using the host network option. And this is going to allow our pods to communicate to each other with the host IP rather than a Kubernetes assigned IP. And this is going to allow our pods to communicate with each other even when, strictly speaking, Kubernetes pod-to-pod communication does not work. We also have no moving parts in this whatsoever. There's nothing dynamic happening. And finally, using the host network option can actually see a relatively nice performance boost, as we are just removing some more layers of indirection. However, if you are in an environment where VMs are constantly being recreated and removed, namely during Kubernetes node upgrades, then this solution is not going to be fantastic for you, as you're going to have to constantly be changing out the various IPs and the certificates minted for those IPs. We're also going to be using up ports on the host machine, which are a limited resource. Solution number 2 is to have external load balancers provisioned for each Cockroach pod. So this is going to see us having a very similar setup to the previous solution. However, rather than routing to these pods directly, or machines directly rather, we're going to be routing first through a load balancer. And this is going to give us that same benefit of being able to work in an environment where pod-to-pod communication isn't really possible, as we'll just be routing over the public internet. And this is also going to be working in situations where we have virtual machines being added and removed from our cluster, as we're really just relying on the load balancer IP addresses to stay the same in this situation. However, it does require that you have load balancers accessible, which are not always available for on-prem deployments. It can also be kind of pricey to run that many load balancers. And on top of that, we're going to see these same drawbacks from the previous example, where we're going to have to do a good amount of work here and then some additional work as well, just to scale up our cluster, and the fact that we have to be creating more load balancers and more certs and hunting down and manually editing configuration files. And last but not least, we have an extra hop on our data path, which most of the time is not going to matter, but it's something to keep in mind. Solution number 3 is to use pod IPs directly. So this does assume that we have pod-to-pod connectivity across our clusters, and we're really going to be relying on CockroachDB's assignment of a node ID to individual nodes that is separate from the IP addresses. So as we delete and recreate our pods and they come back with different IP addresses, Cockroach is still going to be able to recognize them as the node that they previously were. And finally, to actually get our pods kind of bootstrapped together, we're going to be creating an internal load balancer and using that as our join flag. This is just going to start the initial connectivity of our cluster, and it won't be used on the data path, as CockroachDB has a gossip protocol that is going to be sharing the IPs of the various nodes in the cluster. So on the pros side, we have very little overhead on the data path. It's just the normal Docker overhead, and we're pretty resilient to having hosts added and removed, as we have the ability to keep track of our individual nodes externally of the IP addresses assigned to them. And all in all, the configuration work here is not too bad. All we need to do is create these services and specify them in our join flag. On the cons, however, we do need to have pod-to-pod communication enabled. And unfortunately, as we are connecting directly with IP addresses, it's going to be a bit tricky to be minting TLS certificates for these pods. Solution number 4 is doing some DNS shenanigans effectively. So how can we add persistent names to the previous solutions so that we don't have the need to be constantly recreating these TLS certificates for every pod when it gets restarted? And what we're going to be doing here is taking a look at Coop DNS. So the standard path for Coop DNS is that a pod will make a DNS request. It's going to go to Coop DNS. Coop DNS is going to refer to the API server, look up the services, and then send back that information to the pod. So option number 1 is, instead of Coop DNS, we can use Core DNS, as Core DNS is going to allow much more configuration, and it's also going to let us have the ability to just point at multiple Kubernetes API servers. And that's just going to give us the ability to reference pods and other Kubernetes clusters, again, supposing that we have this pod-to-pod communication enabled. And swapping out Core DNS on managed service offerings is doable. In some cases, it's a bit involved, but it's not the worst thing in the entire world. And this is also the solution that we're currently using on Cockroach Cloud. Option number 2 here, if you're not interested in running Core DNS, is called DNS chaining, and we're going to be using Kubernetes stub domains. So stub domains allow us to say, for this certain domain or set of domains, don't refer to the Coop API server for the lookup. Instead, pass this along to another DNS server. And we can do this by creating a config map in the Coop system namespace called Coop DNS. That is our list of domains and the addresses to look them up at. And what this is going to effectively do here is, when pods in cluster 1 make a request for pods in cluster 2. Coop DNS will just forward this on to the Coop DNS in cluster 2. And the pros here are, again, we don't have any overhead in our data path. We're fairly resilient to changes being made in hosts, as we're just leveraging Kubernetes service discovery here, and we don't have to be running any extra controllers in the cluster. However, we do need pod-to-pod communication across clusters, and we may need to set up load balancing for our DNS servers in some cases, which is not super well supported in most cloud environments. Solution number 5 is Istio. Istio is a service mesh that we can also coerce into providing pod-to-pod communication as long as we have service entries for them, both in Istio and in Kubernetes. This diagram is a very brief snapshot into what that setup would look like, and it is taken directly off of the Istio website, so thank you to them for setting this up. We're not going to dive too much deeper into how exactly this setup works. We're just going to briefly cover the pros and cons of that. So the pros are this solves the pod-to-pod connectivity issue for us via Envoy gateways. It also solves our naming issue by introducing a .global TLD as opposed to the .local TLD that is available in our single region clusters. However, as with Istio the setup process is fairly involved, and the software that you're going to be running on it needs to support intra-cluster and inter-cluster IP addresses, as that is the price of using the Envoy gateways. Alternatively, they could rely on constantly doing DNS lookups. Conveniently, Cockroach DB does support having multiple IP addresses for a single node. And final point with a pretty big asterisk next to it is that there will need to be some form of manual replication of these service definitions across your clusters. The reason for this asterisk is because of a companion software called Admiral. Now, Admiral is a fairly new software, but it takes charge of providing synchronization between various Istio deployments, which removes the necessity of having to do that manual sync between the two. I can't say that I've dove very deeply into this, but it seems like a very promising option. However, doing the manual replication does not seem like the worst stopgap in the meantime. Here we are on to solution number 6. I promise there's only one more, and I misplaced my glasses, so yeah. Anyways, so solution number 6 is Submariner or other related tools. So what Submariner does is it networks together multiple clusters by setting up IPsec tunnels between the two, or 3 or 4, however many you decide to put together. And while it's not ready for production use just yet, I wanted to highlight that more options like this are steadily becoming available, and more likely than not, they're going to become easier to set up as well. And finally, we have the last solution, RollYourOwn. You can do whatever you want to get multi-cluster networking working. You can set up 2 Kubernetes clusters and just slap in your own DNS and whatever. However, this isn't really something that we can recommend to people. This isn't something that we would use ourselves, just because it's not something that's super easy to redo, and it's going to be not entirely, but it's going to be fairly dependent on what you're doing. Some cases this will work great, other cases it's going to be a bit more difficult to have something you're happy with, really. In case you didn't really pull this away from the talk, what we really want people to walk away knowing is that multi-cluster networking is still kind of a minefield. It's a bit difficult to set up, and you're going to have to do a little bit of digging around through the various solutions to see what's going to be matching your case the best. And new solutions are still popping up every day, and it's going to get continually easier. So there's definitely a light at the end of this tunnel, but we are still unfortunately in the tunnel. And with that, that's all I had today. Thank you everyone for tuning in. If you would like any more information, please check out any of the links on this slide, or feel free to reach out to me on Twitter or GitHub.